Welcome, welcome. So I see there aren't any questions that anyone has. So I'm going to continue where we left off in our last discussion. If you do have questions, please text them over in the Discord chat or unmute yourself and speak up. If you're watching the video later rather than in real time, obviously that's fine and encouraged. Feel free to message me questions anytime when you are watching this, if you have any, if something I say doesn't make sense, etc. So we were talking about carboxylic acids, and we finished up last time talking about how to make carboxylic acids. And I forgot to share my screen. And also, I gotta get this cat out of here because he won't behave. Oh, I'm so sorry. Alright. I'm going to go ahead and jump back in. Thank you, Amy, for reminding me to share my screen. So we were talking about how to form carboxylic acids last week, and now we're going to talk about what are some of the reactions that carboxylic acids undergo. We know that they act as acids. We know that this is a protic hydrogen because when the electrons stay behind on the oxygen, it's stabilized through resonance. So anything that's even weakly basic can pick up this proton. And one reaction that carboxylic acids react, one reagent they react with is lithium aluminum hydride. And the first thing that would definitely happen here would be a quick proton transfer. So if you treat any carboxylic acid with lithium aluminum hydride, you're going to very quickly see a bubbling, and that forms when this hydride picks up a proton, and that produces hydrogen gas that bubbles out of the reaction. So we're going to need excess of this, typically, to make sure we get a full reaction. After the proton transfer, though, I've got a negative charge here, stabilized through resonance. And since the aluminum still has these bonds where the hydrogen is a lot more electronegative than aluminum, and the aluminum needs to get rid of all those electrons to make its 3+ noble gas configuration, another hydride could be lost, or if you're using excess, another molecule of LEH could deliver a hydride to the carbonyl carbon, right? So that is not going to happen as often as the proton transfer. So we expect the proton transfer having a much lower activation energy required to be happening much faster. But then once the proton's transferred, even though it's already negative, another pair of electrons can come in here and shift these electrons up to this oxygen. And so that kind of creates two negatives on the same structure. So the aluminum with its positive will come in and start to share these electrons. Now this bond is not very covalent, it's mostly ionic. And the oxygen is a lot more electronegative than the aluminum. So there's a very large partial negative here, and the two negatives on one structure are pretty unstable, but the aluminum does attract those electrons to help stabilize the extra negative that would exist there when this electron pair shifts up to the oxygen. So once that occurs, this electron pair will swing in and push that oxygen out as a leaving group. It's not a very good leaving group because once it leaves, it gives you this, which is a negative. And since the oxygen's way more electronegative than aluminum, it's also attracting these electrons, which gives it even more negative beyond that. So its quantity of charge is somewhere between -1 and -2. So that's a lot of charge from one atom. It's not that stable. It's still more stable, though, than this negative on a hydrogen. So this process is still driven forward thermodynamically by the products being more stable, hydrogen gas, this product, they're all more stable than the initial LAH reactant. And that's what's nice about LAH is it's so unstable and reactive. It will react with a variety of different compounds. It will react as a base and pick up any proton that's available. It will act as a nucleophile and attack virtually any carbonyl carbon that's available. So that produces an aldehyde, which we know from our experience discussing ketones and aldehydes, is still electrophilic, and another hydride can still attack it. So that would continue to react, and that's another reason why we need excess LAH in this example. So another LAH would deliver a hydride there, shifting electrons up here. This negative is relatively unstable, but still, again, much more stable to put the negative on the highly electronegative oxygen than on the very small hydrogen, where it creates a massive charge imbalance, or on the aluminum that's extremely low in electronegativity. That oxygen would pick up a proton, so this would be added in the second step, right? So up until this point here, this all happens upon the addition of excess LAH. It gets you to this intermediate, and all your molecules will be converted into that by the excess LAH, and they would start to build up in solution until you're confident that they've all been reacted for the most part, and then you'd add H3O plus maybe the next day or something like that to protonate that and give you an alcohol. So this gives you a primary alcohol. So the overall reaction here is the carboxylic acid treated with excess LAH in one step, and then H3O plus and water in a second step gives this primary alcohol. So it's a full reduction of the carbonyl carbon as reduced as it can be in the presence of LAH. Can the reduction be stopped at the aldehyde? The answer is no. An aldehyde is very reactive to our LAH. So even if we didn't use excess, when some of the LAH reacts here and produces the aldehyde, some of the molecules are going to undergo that before others have even had a chance to react, probably. And the ones that have formed into aldehydes will react with any LAH that's there. So there's really no way to stop this reaction at the aldehyde. It will pretty much always keep going in the presence of LAH to this alkoxide, and then the H0 plus that's added will convert that into a primary alcohol. So there's a new reaction. I know y'all love learning new reactions, because it's just one more reaction that you might be tested on. So enjoy that one. Similar reaction can occur with borane. It's a more mild reducing agent. So the borane won't react with every carbonyl. Borane is actually, it's less reactive. So if you recall, the ketone moiety we talked about, that is reactive toward sodium borohydride. And the borohydride is more reactive because there's a negative charge there on the hydride, similar, well, on the boron actually, but the hydride's more electronegative, so there's a large partial negative on that hydrogen. The full negative on the structure means that it will readily lose the hydride, and that can attack here, just like LAH. So sodium borohydride is not quite as strong as LAH, but it's still strong enough to reduce aldehydes and ketones, pushing electrons up to the oxygen, and then that would eventually pick up a proton and produce an alcohol. This borane reagent is even less reactive, though, and it won't react with carbonyls when they're in the form of aldehydes or ketones, and so we expect the borane reagent to only react with the carboxylic acid, and so that's an alternative approach toward that reduction. So in this particular example, since we have two sites that are both reactive toward LAH, if I wanted to reduce both of them, and treat that with LAH, the LAH would reduce this ketone to an alcohol, and it would reduce the carboxylic acid to an alcohol. So if I wanted to reduce each of those carbonyls, I would use LAH. So this borane reagent is really only useful if you want to selectively reduce a carboxylic acid and not an aldehyde or ketone that would also be present somewhere on the structure. So that's a little bit of detail relating to those reactions. And so those are really the only two new reactions that we're going to be looking at carboxylic acids undergoing, other than reactions that replace the OH group of the carboxylic acid with some other electronegative atom or grouping of atoms. So when a reduction occurs, the oxidation number decreases or is reduced. And when we're talking about this reaction here where the carboxylic acid is undergoing a reduction using, we could use LAH here, we could use this borane reagent. We determine the oxidation state for the carbon based on how many electrons it has around it. And whenever it's bonded to something more electronegative than it, that's going to attract the electrons away. So this carbon has very few electrons. And so its charge is going to be quite positive. A reduction means that quantity of charge is decreasing or becoming less positive or more negative. So by putting hydrogens on there, that always causes a reduction in the oxidation number because the hydrogens are less electronegative than carbon and allow electrons to shift toward the carbon. So now the carbon it still has a partial positive because the oxygen is pulling electrons away, but not nearly as much as the carbonyl carbon. They're way more partial positive there. So it's not as positive. The quantity of positive is decreased or reducing, and so that's a reduction reaction. So there are many reactions that carboxylic acids undergo where the oxidation number doesn't change. And so just replacing the OH, which attracts electrons, with a different electronegative atom, nitrogen, or maybe a different oxygen that's connected to an R group or some other group, it's still more electronegative than carbon, so it's still attracting the electrons away. So the carbon takes on the same oxidation state, the same quantity of positive charge. So in these reactions, the oxidation number won't change. And so these compounds are called carboxylic acid derivatives. It's like a carboxylic acid because the carbonyl carbon has the same oxidation number. But it's not a carboxylic acid because we have a different grouping of atoms here. An OR, or an OCO double bond, or an N. Nitrogen would also work here. And so if we're only changing the group attached rather than the oxidation number, the new molecule is considered a derivative or something that can be derived from a carboxylic acid just by replacing that OH group with another group. And so that's what we just said here. If I replace it with a halide, it's more electronegative than carbon, and oxygen, another oxygen, and nitrogen. This nitrile is even the same. I've got only one R group, which is the same number here, which is the same number as a carboxylic acid, and all the other atoms attached are more electronegative than carbon. And so they're all pulling electrons away, creating the same oxidation state for that carbon. So every one of these is considered a carboxylic acid derivative. There's also something called a carbonate that this book doesn't really focus on, but just to let you know what that structure looks like. Here is a carbonate. So is a carbonate a carboxylic acid derivative? The book doesn't talk about it. They're not that common. They're relatively reactive, but it also doesn't focus on them in this section because technically they're not a carboxylic acid derivative because they have a different oxidation state for the carbonyl carbon. If if I bond that carbon to exclusively to elements that are more electronegative than it, it's only going to have even more positive. The oxidation state on this carbon is a +4 because it doesn't really have any electrons assigned to it. They're all being pulled away from another atom. So the R group here, at least the R group and the carbon have the same electronegativity, so that carbon is only going to have a +3 oxidation state when at least one of these electrons will be assigned to it. So technically this isn't a carboxylic acid derivative, but it undergoes a lot of the same reactions that carboxylic acid derivatives undergo. So it could have been included in this section if they're focusing more on the reactions that they undergo rather than the oxidation number of the carbonyl carbon. So this next section is somewhat informative, and I usually ask a lot of questions about these types of just slides where you're just showing examples of different functional groups in nature, but I think it's useful to kind of see some of these things and just get a visual for what the structures look like that you might come in contact with in your daily life. So a lot of the esters, which we know are a functional group where there's the components of a carboxylic acid, but instead of a hydrogen here, there's an R group, and there's an R group or a hydrogen here. So with these two R groups here, that functional group is an ester. And esters are pretty common in nature. They're relatively stable. We'll see some reactions that they undergo, especially with water. But a lot of organisms in nature will convert molecules they take up through metabolism into a variety of esters, and some of these are found in fruits. Another common derivative of a carboxylic acid group is known as an amide or amide. These are very common. What type of molecule in nature includes amide linkages? Well, that would be proteins. Proteins occur in every organism. They are long chains of molecules that are connected together through this amide linkage that's highlighted here in gray. So typically, the way to make a protein is to start with an amino acid, which actually, let me pick out one here. Let's just pick out this amino acid here. So that would have this carbon here. There's an R group, and the different amino acids vary depending on what the R group is. It could be, doesn't have to be a carbon, it could be another functional group there as well. So an amine, or an amino group, is usually an NH2, or there could be R's here. So some nitrogen with 3 bonds in a lone pair, if it's bonded to at least one carbon, is an amino group. And amino acids have an amine, and then 2 carbons away, a carboxylic acid. So an individual amino acid has an amine group and a carboxylic acid group. But once that carboxylic acid is chemically bonded to the neighboring carboxylic acids, there's a loss of water. One of these hydrogens is lost, and the OH is lost. And then the nitrogen of one structure bonds to the CO double bond of the neighboring structure, and that's the amide linkage. The CO double bond of this amino acid, the OH is gone, and the CO double bond links to the nitrogen of the neighboring amino acid. So you make a polymer in this way by connecting one amino acid to the next through amide linkages. And that linkage is really just right for organisms to use it to build structures. So, you have some molecular structure that needs to take on some function as an enzyme or to build up some tissue material. You want it to be strong enough where once your body constructs it, it can last for a while, but you also want it to be able to be degraded in times of need if necessary to be used for energy. So the amide linkages are quite strong relative to a lot of other chemical bonds, but they're not so strong that they can't be broken with the right enzymes. So obviously we have evolved enzymes to break and form bonds as needed to convert molecules into the biologically desired chemical structures, and the amide linkage is a very important linkage in that process. And so here's another example of an amide linkage. There's an R group here, an R group here, and so that's the amide linkage. The nitrogen as a group connected directly to a CO double bond. So there's an amide here. We recognize this functional group, ether. Talked about that. We recognize this functional group, which is an amine. We're going to talk more about amines before the semester ends. And so most natural products have lots of different functional groups on the structure. Obviously, there's an aromatic system here as well. So I'm going to go through this naming part pretty quick, I think. Typically, I don't ask you to name structures that are derivatives of carboxylic acids. There's a lot of different derivatives, and they each have their own little nuances involved in naming them. For example, we talked about naming carboxylic acids, and you want to be prepared to name carboxylic acids this week on your exam, since we talked about that last week. You want to do some practice relating to that. But if I want to convert the carboxylic acid into an acid chloride or an acid bromide, I have to, in terms of the nomenclature or naming, I have to change the suffix from ic acid to eel bromide. So acetic acid becomes acetyl bromide, benzoic acid becomes benzoyl bromide. So, that's the rules for naming carboxylic acid halides. We talked about naming this structure as kind of an unusual situation where the carboxylic acid group was not part of the parent chain. It was named as a substituent, and the substituent came at the end of the name instead of in front of the name, which is kind of weird because that's not normal for the nomenclature system. And if you were to name a compound this way, then you would change the suffix accordingly if you were converting the carboxylic acid into an acid chloride. So again, not something I would typically ask about. The anhydride functional group is a useful functional group. We'll see some reactions involving hydrides a little later. Anhydrides. Anhydrides involve, when you're naming anhydrides, you would name that the same way you would the carboxylic acid, but you're replacing the proton with another carbonyl, so you just change the end of the name to anhydride. So that's pretty straightforward adjustment to the naming system for anhydrides. That's when you have a symmetrical anhydride, I should say, when the two sides of the anhydride, the two groups attached here, are identical. Then it's a simple replacement of the word acid with anhydride. If you have an asymmetrical anhydride where the R group on one side of the anhydride, which is this part of the structure, if the R group over here, which is an aromatic ring, is obviously different from the methyl group, any two R groups that are different is going to affect the naming. So you would have to recognize that one part of the anhydride over here comes from benzoic acid, just taking away the hydrogen, and the other side comes from acetic acid. So if we take away the hydrogen and the OH, so we're basically removing a water molecule, and then we connect this oxygen up here, that will make the anhydride. So this anhydride is made from benzoic acid and acetic acid. So it's acetic, benzoic, anhydride. And as would be listed alphabetically. When you're naming an ester, often what you would do is you would put the R group that's bonded to the oxygen of the ester directly to the oxygen as a substituent, and then name the rest of the ester as if it were a carboxylic acid. So this, if this were a carboxylic acid, and I had an OH here instead of an OR, it'd be acetic acid. So we take the ic acid off and we add the suffix ate. So an acetate is when I remove this hydrogen. If I just wrote the word acetate, that implies it's the conjugate base of acetic acid. But if it's an ethyl acetate, that means there's an ethyl group bonded to that oxygen. So similarly over here, this would be a cyclohexane carboxylic acid if there were an OH here, but since there's a methyl, it's a methyl cyclohexane carboxylate instead of carboxylic acid. Amides, similar situation. We're going to replace the ic acid suffix with the amide. So acetic acid becomes acetamide. Benzoic acid becomes benzamide. Again, I'm not going to probably give you a bunch of naming examples for the carboxylic acid derivatives. One thing that you should know is often when a substituent is attached to a nitrogen rather than a carbon, instead of giving it a number, when naming it as a substituent, it's often given the letter N. And so if I had my parent chain here, the parent acetamide implies that I have acetic acid, and that I'm replacing the OH of the acetic acid with an amide, which is the nitrogen. The acetic acid has a methyl group here bonded to the COOH. So basically I'm taking acetic acid, I'm getting rid of the OH and replacing it with the nitrogen, and then there's an extra methyl on the nitrogen. So N-methyl means specifically that there's a methyl group. It doesn't matter which hydrogen I show the methyl group on, but put the methyl group on the nitrogen. If there's more than one methyl group on the nitrogen, just like if there's more than one methyl group on the parent chain, I need a number for each, and I need the prefix to indicate there are two. But in this case, I wouldn't put a number because they're both on a nitrogen. So instead of like 2,3-dimethyl, it would be NN-dimethyl to name where those substituents are. And then again, the parent, this would be acetic acid. If we had an OH here, including the nitrogen, implies I have acetamide because it's an amide or amide functional group. In terms of the CN triple bond, if you're naming those carboxylic acid derivatives, the idea here is the carbonyl carbon isn't really even a carbonyl anymore, but since its oxidation number isn't changing because there's the same number of bonds it has to electronegative atoms as this one does, because they're all to the nitrogen versus the oxygen. So here again we're changing the suffix and replacing it with a different suffix. So acetic acid becomes acetonitrile. Benzoic acid becomes benzonitrile. And so the nitrile is the way to describe a CN as a parent, if it's part of the parent chain. And again, we're replacing the ic acid with some other suffix if we're changing a carboxylic acid into one of its derivatives. All right, so the naming part for the carboxylic acid derivative is not usually something we focus much on or really ask you questions about too much. But the carboxylic acid derivatives are very important as electrophiles. And they will react as electrophiles with different strengths kinetically and thermodynamically. And so that we want to focus on that a fair amount. So clearly the carbonyl carbon is the most electrophilic site here, as we've been saying about ketones and aldehydes and about carboxylic acids, because the CO double bond involves such a big electronegativity difference. Through induction, the electrons are pulled away. That creates a nice partial positive for a nucleophile to be attracted to. Also, so beyond induction, there's also resonance. If the electrons swing up, and that goes for any one of these four, you have a negative there and a positive here. That increases the quantity of positive, even though it's a minor contributor. It does contribute so much, which increases the quantity of positive here, which helps to attract the nucleophile in. So there's resonance. In general, there's a lack of sterics, and that goes for really any carbonyl carbon in general, because if it's a carbonyl carbon, it's flat. And if we look at that flat carbon there and the orbitals that are involved, there's a p orbital overlapping with this p orbital to make the pi bond. And when the nucleophile comes in with its orbital, it's going to face that other p orbital head on. This carbon is going to rehybridize into an sp3 hybridized carbon, so that some head-on orbital overlap can occur there. And since the carbon is flat and the angles are only 120 and there's nothing above it or below it, the nucleophile could come in from above or from below to, once the carbon rehybridizes, do a head-on orbital overlap and make a new sigma bond. So it's easier for the nucleophile to attack in general because it's flat and there's not much sterics blocking it from coming in and overlapping head-on with the p orbital that's there as the p orbital rehybridizes into an sp3 orbital. So that's all true in general for any carbonyl carbon. So we want to also get into some of the subtle differences, though, when we put different groups on the carbonyl carbon. How's it going to affect the electrophilic nature of that carbonyl carbon? And so these factors we've already talked about are important, but now we also have in red in each one of these a leaving group, and so that's going to affect things. So we want to also be careful to discuss which of these factors affect the kinetics versus which affect the thermodynamics. And so we have to know what reaction we're talking about if we're looking at the thermodynamics, because we're comparing the reactants versus the products. In kinetics, we don't really even need to know what the products are, because they're irrelevant. If we're just interested in, so let's talk about the kinetics first. If we're just interested in the kinetics, what we're interested in is how often can how often can a nucleophile attack? How often will it attack? And will that attack lead to a relatively low energy activation energy so that pathway can occur often? So when it comes to induction, what we're thinking about here, if we're talking about the kinetics, is how high in energy is this reactant, right? Because when it comes to kinetics, what we're interested in is if the reactants are already relatively high in energy and the transition state isn't much higher in energy, then we can get to the transition state and form intermediates and then eventually get to the products. We don't really care what happens next, because what we care about is how much energy goes in to the slow step. That's going to determine how often these collisions can get through this pathway. So induction is relevant because if the atom attached is more electronegative than carbon, which each of these is, it pulls electrons away from carbon, in addition to the induction that we've already talked about from this oxygen pulling electrons away from carbon. So just from induction, this carbon in each one of these cases is carrying a lot of partial positive. Even more so here and here, because oxygen's more electronegative than chlorine or nitrogen. So the more partial positive there is, the more unstable this carbon is. Right? I've got too much positive causing repulsion, not enough negative to balance out the positive that's there, and so it's relatively high in energy. Right? So that helps the kinetics, creating more positive on the carbonyl carbon where the nucleophile is going to attack, makes it high in energy to begin with because there's lots of positive charge there that's not stable and high in free energy or potential energy to begin with. We talked about the resonance. We know that the oxygen can also pull electrons away from the carbon in each one of these cases, making even more partial positive there. So that raises the energy of the reactants even more. But now we have other atoms nearby that can also engage in resonance. So what we want to think about here is when these electrons swing up onto that oxygen and give us this minor resonance contributor with a positive on the carbon that's contributing to making this unstable with so much positive on that carbon, if the other element can shift electrons in to stabilize that positive, that would lower the energy of the reactant and make it harder to get to the transition state because there'd be a bigger activation energy necessary to get from that lower starting point up to the transition state. It wouldn't happen as often. It would be less reactive kinetically the more stable you make the carbonyl carbon. And so this is where we actually start to see some differences. The acid halide stands out as the most reactive kinetically. And when I was reading your quiz answers, y'all did a great job with this, recognizing that the chloride or bromide that you would have here as a halide or iodide, it's not going to be able to contribute much electron density and resonance because shifting electrons in here requires the p orbital of the carbon to overlap with the p orbital of the chlorine, but it's a different energy level. So when the p orbitals are different energy levels and sizes, there's a mismatch and pretty ineffective orbital overlap. So the oxygen can readily shift electrons in there through resonance, and so can the nitrogen to help balance the quantity of positive that's on the carbon. And if we just look at the nitrogen example, we could say, well, if these electrons swing up first, that would give us this resonance contributor. But if these electrons swing in there, it gives us another resonance contributor, which is even more major because, at least in this one, all the noble gas configurations are complete versus here where the carbon doesn't have a complete noble gas configuration. So in this case, this resonance contributor is more major than the one with the positive on the carbon. Obviously, the one with no formal charge at all is the most major contributor. And so based on the resonance, there isn't going to be much positive on this carbon. And so, or in other words, because the nitrogen shifts electrons in there to stabilize that positive, it stabilizes it and lowers its energy. So the reaction won't happen as often because it's starting at a lower energy point. And then sterics is also relevant, and we see some differences here. Typically, let me get rid of some of this stuff. Typically, when it comes to sterics, if we're dealing with a halide, that's a really small atom. It's a single atom, chlorine, bromine, iodine. Those are relatively big atoms, but still only one atom. So whatever the nucleophile is, as it comes in there and collides and pushes electrons up in this first slow step, we've already talked about how there's so much positive here that it starts pretty high in energy. But we also want to talk about the transition state energy. And the transition state energy shouldn't be much higher, especially if during the transition state there's not much sterics. And so even if I have a big bulky nucleophile coming in here, since the chlorine is so small, the electron clouds won't overlap much and create much repulsion during the collision, so the transition state energy isn't very high, and the reaction will be able to happen often. If there's a big bulky group here, or if this R group is big, or maybe instead of having two hydrogens, there's a hydrogen in an R group, and I've got a big bulky group here, that's going to block the nucleophile from coming in. It's not just going to block it, but if the nucleophile does attack, during the attack and this electron cloud and this electron cloud, they get close and start repelling, that means the transition state for these three is going to be significantly higher because of the repulsion, the steric repulsion that occurs during the transition state is going to make that unstable. So those reactions require more energy, even though the reactant, well, the reactant's also starting lower energy. So it requires a lot more energy to get up there. So kinetically, the sterics associated with these ones that have larger R groups are going to slow the process down and make it happen less often. I'm going to have to pause this for 1 second. I just heard a crazy sound happening in my house. Zoom. So what we're saying is, from a kinetic perspective, these three factors are important, and they all explain why the acid halide reacts kinetically much more often than the other three. The quality of the leaving group is more of a thermodynamic consideration. So let's talk about thermodynamics. So when it comes to thermodynamics, we have to look at the equilibrium that's forming. So, all right, so we talked about this, and we talked about this. We talked about the sterics. Let's talk about the quality of the leaving group and the thermodynamics. So, if we have an acid, carboxylic acid derivative, maybe there's a halide here. Other carboxylic acid derivatives, maybe there's an OR group here. So we'll look at these two first. If I have some nucleophile come in, it's going to come in, it's swing electrons up to the oxygen. When they swing back down, it's going to push out the leaving group. So the product, if we're just looking at thermodynamics, we're really only interested in the reactants versus the products rather than the pathway that occurs. The product will involve the nucleophile there, and the chloride would become the leaving group. Same thing here. If this leaving group leaves, I'll have a negative on an oxygen. So the quality of the leaving group is a major factor when it comes to the thermodynamics. It's the biggest factor when it comes to the thermodynamics. You know, we can say the same factors that affect the energy of the reactant, the induction and lack of resonance from the halide, creating a larger partial positive here than we have here, because even though the oxygen attracts more electrons through induction, it does also donate electrons through resonance, which the chlorine can't really do because of the orbital mismatch. So this one does also start higher in energy. And so if we're looking at the reaction coordinate diagram for this one versus this one starts higher in energy, maybe than this one. And the chloride, being such a large atom, can really stabilize a negative charge very effectively. Its products are going to be much lower in energy than this one here. So the formal negative here on the oxygen, being much smaller atoms, not going to be nearly as low in energy. So just looking at, not interested even in the kinetics at all, just the thermodynamics for now, the value for delta G is much more likely to be negative here. It might not even be negative there. It might be closer to 0 or even positive for that process. And so that's looking at the enthalpy part of the equation, but we also want to think about entropy. Right? We know when we're looking at equilibrium, what affects which side the equilibrium favors is the sign and magnitude of delta G. And delta G is affected both by the stability difference, which we talked about here, as well as the entropy difference. But in these cases, the entropy term is usually pretty close to 0 because you've got 2 reactants and 2 products, and the amount of variety or entropy associated with the positioning and movement of the particles both before and after the reaction are pretty similar since you have the same number of moles of particles on both sides. So since the entropy term is usually negligible here, all we have to do is look at enthalpy to judge which side is favored. So that explains why the thermodynamics favor the forward reaction so much when you start with an acid halide, because it starts off relatively unstable and it produces an especially stable leaving group compared to the other ones. So let's look at, we talked about the kinetics. Let's look at all at the other two real quick then. Right? So we could also include the carboxylic acid. So we have the carboxylic acid, we have the acid halide, we have an ester, we have an anhydride, and we have an amide. So often the amide is an NH2, sometimes it's an NR with an H, and sometimes it's got 2 R groups. So if we're just looking at the thermodynamics, we're talking about in each case reacting with the nucleophile and letting it reach equilibrium for each one of these and looking at the products. And the products would involve the nucleophile coming in and replacing the leaving group. The leaving group here would be an OH. The leaving group here, so this is going to be the same in each one of these cases. The leaving group here is going to be a chloride or a bromide or an iodide. The leaving group here is going to be an OR. The leaving group here, so the nucleophile is going to come in, push electrons up. When they swing back down, it'll push the leaving group out. So the leaving group there is going to be an CO double bond R. And here, when the leaving group leaves, I'm going to get a negative on a nitrogen. So, as we were saying, thermodynamically, the entropy difference is minimal because I've got 2 moles of reactants and 2 moles of products. These reactants are all pretty similar in energy, but we did say that the acid halide is the highest in energy. And so if we're strictly looking at delta G, which is what governs the equilibrium and the thermodynamics, if we start off higher in energy, high potential energy to begin with, or high free energy to begin with, it's going to make delta G more negative. If the products are lower, it's going to, make it more likely the products are significantly lower in energy and make delta G more negative. So it's not just about the stability of the leaving group, it's also in part about the stability of the reactants. So this reactant is the highest in energy, and its leaving group is the lowest in energy and most stable. So if we start with a high energy reactant and we get a very low energy product, that's when delta G is going to be most negative, and that's when the process is going to be most product favored versus reactants. And so which one would be next most product favored? Well, it would be the anhydride. So even though the oxygen here can donate electrons here through resonance to help stabilize the positive. So the reactant maybe doesn't start quite as high in energy. The product, leaving group, is also stabilized by resonance. So it's pretty stable. Not as stable as the larger atom, which can stabilize a negative a lot better than the smaller atom, but the resonance does help to stabilize it a lot. So it's, it might be here, so still a negative delta G, but maybe not as negative, obviously. Right, so this one is still going to be pretty product favored, but maybe not quite as much as the acid halide. These two are pretty similar. They both have oxygens that could shift electrons in and stabilize the carbonyl through resonance. They both produce negatively charged oxygens as the leaving group that aren't really well stabilized by induction or resonance. The difference is when you have a bulky R group here, it's going to block out solvent from coming in and forming nice attractions to stabilize the negative. So because of the lack of solvation, this leaving group's not quite as good as an OH minus. So depending on the strength of the nucleophile here, we could be talking about a situation that maybe isn't even product favored. We need a strong nucleophile here that's really unstable if we want the products to be more stable than that, because the products with the negative on an oxygen, especially when it has a big R group on it, are not going to be very stable. And so we don't know which direction these two equilibria are going to be facing. It's going to depend on how unstable the nucleophile is. And then lastly, this last one is typically not usually product favorite. I mean, it is sometimes, but not usually. I mean, if I have a really strong nucleophile, it can come in there and push that leaving group out. But a negatively charged nitrogen is pretty unstable. It's one of the things we've seen often where we have a negative charge that's really quite unstable, and it would often come back in and start sharing those electrons due to the small size of that nitrogen. So if my nucleophile is like even smaller than a nitrogen and equally negative or more negative, well, then it's probably even less stable, and that would favor potentially the product side in an equilibrium. But because the nitrogen is relatively unstable at the negative, depending on how unstable the nucleophile is, it has to be even more unstable to make a negative delta G. And if it's not, and I have a positive delta G, it's not going to be a product favored process. So when we're looking at thermodynamics, any way we can increase the initial energy of the reactant and decrease the energy of the product, that will give some more product favored process. So hopefully that helps clarify the two quiz questions for y'all, and I will definitely be giving you comments on your individual Google Docs to help you with that as well after lecture. So as we were saying, the amides are the least reactive of the acid carboxylic acid derivatives, and one, because nitrogen's not as electronegative as oxygen. It doesn't really pull as much electron density away. Plus, since the nitrogen can donate electrons in, this is a more significant contributor than even this one, because we have complete noble gas configurations here. And so the nitrogen really helps to stabilize that carbon by taking on some of the positive that would normally exist on the carbon. So both the electronegativity of the nitrogen not being extremely high, pulling electrons away through induction moderately instead of strongly, and the resonance mean that this carbon doesn't have as much partial positive as it would have for the other carboxylic acid derivatives. So as we're saying, it starts kind of lower in energy to begin with, and after the reaction, because this nitrogen would have to be a leaving group, which is pretty unstable, it's got pretty unstable leaving group, so it might not even really be product favorite from a thermodynamic perspective. From a kinetic perspective as well, because this energy is pretty low to begin with, to get to the transition state, it might take a lot of energy. So the forward reaction where the nucleophile attacks here might not even happen that often, especially if there are R groups bonded here that are creating sterics and blocking that out. So again, if I ask you a question about this, whether it's about kinetics or thermodynamics, you want to be prepared to discuss these four factors. Kinetics will not include a discussion of the quality of the leaving groups. This is only thermodynamics, because the leaving group is one of the products, and kinetics isn't about products, it's about how often we get to the transition state. But each of these other factors is relevant to both the kinetic and thermodynamics. Well, actually, the sterics isn't really relevant. This is for thermodynamics. This would be really kinetics only. The sterics isn't really that important for the reactants or the products, because both the reactants and the products, as we're showing over here, both the products and the reactants are carbonyls, and so they don't really have much sterics. The sterics is really most relevant during the transition state, where the nucleophile would have to come in here and the leaving group has not yet left. So if the nucleophile is bulky, or this R group is bulky, maybe there's a bulky R group on this oxygen, or bulky R groups if it were nitrogen, all that bulk can make it less stable during the transition state, and that increases the energy of the transition state. So sterics is about kinetics, because it's really only relevant during the transition state where the groups are repelling. And the more sterics there is during the transition state, the less often the process can get through that transition state. So that really slows down. It slows down the kinetics of the process. Since these two factors relate to the stability of the reactants, they affect both the kinetics, or how much activation energy there is needed to get to the transition state, because if the reactants are higher energy, less energy is needed to get to the transition state. And affecting this reactant's energy also affects the thermodynamics, because obviously if the reactants are higher in energy, it's more likely to give you a delta G that's negative when you compare the reactants and products, right? So you want to keep separate the thermodynamics and kinetics, but these two factors do affect both of those. All right, so aldehydes and ketones, they don't undergo this type of substitution that we're talking about now, right? So the reaction we're specifically looking at is what happens when a nucleophile attacks here. Well, it's going to push electrons up. That pretty much it's always going to give this intermediate with a tetrahedral carbon. The carbonyl carbon used to be trigonal planar and flat. Now it's tetrahedral, specifically because the nucleophile brought its electrons in there, is now sharing them, and the leaving group hasn't left yet. So this is the transition state, and this intermediate is where sterics is really important. But then the electron is going to swing back down and push out the leaving group. They could also push out the nucleophile, which means it could go back to the reactants. And so these steps are equilibrium steps. But if it pushes out the leaving group, I get this product here. In the case of aldehydes and ketones, the first step works really nicely, because especially for aldehydes, there's not going to be much sterics here. This oxygen is really pulling electrons away through both induction and resonance to create a large partial positive here. So it's easy for a nucleophile to attack and push these electrons up. When we talked about aldehydes and ketones, we talked about that. We said once this occurs, there are two things that could happen. One, if the nucleophile is also a good leaving group, they could swing back in and push that back out and go back. The other option is for this to just wait, because the R group and the hydrogen are not stable with negative charges on them. You are not going to see the oxygen swing back in and push out an R group or a hydrogen. And so if the nucleophile is also a bad leaving group, like maybe a hydride or a Grignard, bringing in another hydrogen or R group here, and it also can't leave and stabilize a negative. Then the oxygen is stuck with a negative until we later add a source of protons, which it could pick up and become an OH group. So if we're looking at a substitution specifically, this has to be a leaving group in order to go forward. If it's not a good leaving group, it won't leave, and the intermediate will be stuck. And even if it did leave, even if the oxygen did swing electrons in and maybe push out a hydride, if this were a hydride or an R group, then it would just come back in and go back to the intermediate. So it wouldn't be product favored thermodynamically. So even though the hydrogen or R group here, it doesn't really withdraw electrons and increase the quantity of partial positive, it actually donates electrons through induction to stabilize that positive. It can still accept the nucleophile pretty readily. The problem is you can't then push anything out that the nucleophile would end up replacing if there's no other leaving group there. So the quality of the leaving group is the main reason why aldehydes and ketones don't undergo these substitution reactions. All right, so if we do have a decent leaving group, we see this two-step mechanism we just outlined. CO double bonds are relatively stable double bonds, right? So generally we say, well, if we're going to convert a pi bond into a new sigma bond, that should be favored. So then why would the oxygen swing its electrons in and push something out if that's only going to reform a new pi bond, right? Aren't sigma bonds more stable than pi bonds? Right? So as far as that specific factor goes, yeah, a sigma bond would be more stable than a pi bond. But when the nucleophile comes in, you're converting two separate molecules or moles into one mole. So from an entropy perspective, just having it come in and form a new sigma bond, that's nice because sigma bonds are more stable than pi bonds in general. But in this case, forming two molecules into one is a pretty low entropy, and that's not going to be favored from an entropy perspective for that to occur. So because as far as pi bonds go, the CO double bond pi bond is one of the more stable types of pi bonds, there isn't as big of a difference between the stability of the sigma bond versus the pi bond in this case. And so when electrons swing back in and push out the leaving group, now you're forming two separate structures again. That increases the entropy, and that's the main reason why the pi bond reforms. Because as far as pi bonds go, it's not as unstable as CC double bonds, but still less stable than the sigma bond. But the entropy advantage here helps to drive that process forward. So the loss of the leaving group is mainly if the leaving group is a decent leaving group and can stabilize a negative charge pretty well. That will happen mainly because of entropy as a factor when it reaches equilibrium. It won't stay in this form, even though the sigma bond is more stable, because entropy favors this form, especially when you have a pi bond that's not as unstable as many other pi bonds. All right, so let's look at some specifics. Take a look at some specific examples of this nucleophilic substitution on a carboxylic acid derivative. So here we have a nice nucleophile. Oxygen is a pretty small atom. It doesn't stabilize a negative charge very well. So it can attack here. This carbon has a very large partial positive. The chloride is not really helping it. It's only making it more positive by withdrawing electrons, and the ability for it to shift electrons in through resonance is very minimal because of the poor orbital overlap. So the very large partial positive here means this is starting off pretty high in energy. This reactant is also quite high in energy. because the chlorine doesn't create much sterics, and this is flat, and the methoxy group's not too big, it can come in there, attack. During the transition state, there's not much steric hindrance, so the transition state isn't really much higher in energy from the reactants. So kinetically, this looks really very likely to attack. Once it attacks and the electrons swing up here to form this intermediate, the intermediate would be a little bit unstable because of the negative on this oxygen. But we already had a negative to begin with. So the problem here is this oxygen is surrounded by more stuff, blocking out the solvent from stabilizing it with whatever the solvent's partial positive is, versus over here being much smaller, more solvent can solvate that and form attractions to it. So because the negative charge won't be quite as stable here as over here, it's going to be a little bit higher in energy when the intermediate forms than the reactants. And if we're looking at free energy, there'd be an even bigger difference. It might look more like this, because with only 1 mole here versus 2 moles to begin with, the entropy of this intermediate is pretty low, which means its free energy is going to be relatively high. So that first step is the slow step. It's not generally favored, even though we're converting a pi into a sigma, because of the entropy and the sterics around the oxygen, making it difficult to stabilize that with solvent. So because that's a little bit higher in energy, it's going to swing electrons in and push out whatever the better leaving group is. It could push out the OMe, which would just go back to the reactants. But then that could come in and attack again, and eventually the chloride could get pushed out. Since the chloride is especially stable with the negative, and now we're back to 2 moles instead of 1, that second step is going to be quite favored. And so overall, this process produces a more stable carbonyl, because now there's some resonance to help stabilize the partial positive, which we really didn't have with the chloride. It produces an especially stable negative, and it produces entropically favored molecules, since there are more moles of them than we would have if everything stuck together in the form of this intermediate. The main thing here driving this forward is the stability of the leaving group. And so that's why, I might even make that even more dramatic to show how stable the products are with the negative there versus the intermediate or the reactants with the negative on an oxygen. So acid chlorides are great for acting as leaving groups, and you can bring in almost any nucleophile to come in and replace them. If I ask you to draw the mechanism, do not make it look like an SN2 though, because in an SN2, the nucleophile has to come in from the back side in the same plane where the leaving group is. And that will not work on an sp2 hybridized carbon because of sterics and because of, well, mainly because the orbitals don't allow for the correct orbital overlap. We were talking about this earlier. We said what has to happen here is this sp3 orbital has to overlap head-on with the p orbital that's coming in and out of the plane of the paper here. So the OMe has to either attack from above on the top part of this head-on, or down here on the bottom part head-on. It can't come in on the same plane as the leaving group and do a backside attack, because there's no orbital for it to come in and overlap with. And so because of the way the orbital overlap has to occur, it can't be an SN2 mechanism. It has to come in first and push electrons up, as we saw on the last slide. So in this particular case, it worked quite well. We had a negatively charged nucleophile, a strong nucleophile. We could also say that's basic because of the negative charge. And under basic conditions, what did we see? A negative we started with, a negative that formed, and we ended with a negative. And that's a pattern that you can look for to help you with these mechanisms. If you're under basic conditions, you'll almost never form a positive, because if you have negatives, they would quickly react with any positives that form, and that would be really unstable to form positives in the presence of a negative, or really unlikely, I should say. So if you're under basic conditions, you almost always have a negative throughout the mechanism. Well, we're going to see some examples where we're under acidic conditions, right? Under acidic conditions means we've got lots of protons around. So maybe the carbonyl would start by picking up a proton, in which case we would end up with positively charged intermediates. We can't mix negatively charged compounds with positively charged compounds because they just react directly with one another, right? So you might say, well, what if there wasn't enough positive here? Well, if you took this acid chloride and reacted it with H+, it would pick up that proton. The oxygen would use a lone pair to pick up that proton. That would make it positive. And that would mean that the resonance where the oxygen's pulling electrons up would be much more significant. And so that would also increase the amount of positive at the carbonyl carbon. And make it much easier for the nucleophile to attack. But you really can't have both of those things going on. You can't have the best of both worlds in this situation. You can't make it the best electrophile it can be by protonating it and giving it a large amount of positive to attract the nucleophile in. And also use a really strong nucleophile, because if you do, the nucleophile will usually also be a really good base, and it would just go for the proton, which defeats the purpose of adding the proton, right? So what we're saying down here is you really have to make a choice. You're either going to use the proton to make it a better electrophile, and you would only do that if you have a weak nucleophile that can't pick up the proton. Or if you have a strong nucleophile, there's no point in adding a proton because the nucleophile would just grab it and then it wouldn't be strong anymore because it would pick up a proton and be protonated. So in that case, you just have to use a carbonyl that's electrophilic enough to attract that strong nucleophile in. And it should work. If the nucleophile is strong enough, it should be able to just attack, as we showed over here, attack and push electrons up and go through the rest of that mechanism. All right, so let's take a look at some examples, some more examples, lots of examples of this type of reaction. So here I've got an ester, and I'm reacting with water under acidic conditions. So if I'm thinking about the mechanism, what's the most likely pathway that this is going to go through? One thing I want to look at is I don't expect a nucleophilic attack to occur if both of my reactants are neutral. So the first step will not be a nucleophilic attack if both reactants are neutral. And that's because they're probably both relatively weak. Neither has a charge, so I really only have a partial positive at this carbonyl. The water's neutral, I mean it has a partial negative, so there is an attraction, but since they're both neutral, neither is really unstable. That means collectively they're starting at a pretty stable, pretty low energy state. And if the nucleophile here were to attack and push these electrons up and get to the first intermediate, I would suddenly have two formal charges, which means that would be a really unstable intermediate, and the transition state on the way to forming it would be even more unstable, so this would almost never be able to go forward. So when the electrophile and the nucleophile are both low in energy, due to both being neutral, I can't really get the reaction to happen very readily. So that is why I need to either be under acidic conditions or under basic conditions. So we're going to examine both of those possibilities. So let's imagine we are under acidic conditions. So we're adding some strong acid, some sulfuric acid or something to provide some H+ that the water molecule is going to pick up. So really this is a combination of H2O, and some of the water will pick up that proton, so we'll have some H2O, and we'll also have some H3O+. So when the ester comes in contact with that, the first thing that's going to happen is the ester is going to pick up that proton and become protonated. And now this was a good electrophile. This is a great electrophile. It's fully positively charged, and there's a major contributor now where the electrons swing up here and give a lot of positive on the carbon in addition to what's normally there just from the induction of these elements pulling electrons away. So this is very reactive. It's got a full positive, it's not very stable, and so it starts off much higher in energy than where it started off when it was neutral. So now that there's a positive charge, already it's a lot higher in energy to begin with, and now when this water attacks and pushes these electrons up to form the intermediate, now the intermediate only has one positive. So while it's more sterics, probably it's harder for this molecule to stabilize its positive with solvation, and there's no resonance to stabilize it like there is resonance to stabilize this one. So it's still significantly higher energy than the reactant. Also, I've got 2 moles here versus 1 mole here. So entropy-wise, the reactants are favored as well. But the intermediate's favored, at least because there's a sigma bond versus a pi, so that helps it stabilize it a little bit compared to the reactants. So there's all these factors involved. But the key thing here is there isn't a huge difference in energy between these two. So this is the slow step. And we're really making the slow step happen a lot more often by first protonating this. So the energy difference between the protonated reactants and the intermediate is not that big of a difference. So this pathway can happen fairly often. So what happens in the rest of the mechanism? Well, as we said, the electrons will swing back in and push out a leaving group. But if they swing back in and push out the best leaving group now, which would be this oxygen, since it's positive, it's pulling these electrons away really strongly, that would just go back to the reactants. So what else can happen with this? Well, let's see. I need to draw it out here. So there'd be a couple proton transfers, right? We've got H3O plus around, we've got water around. So this pair of electrons would pick off a proton from the H3O plus. And we know that acid-base reactions happen quickly, back and forth. They're very reversible, they're very fast. So picking up this proton can happen, maybe it gives the proton back, right? That could happen back and forth. A water molecule could also easily, once in a while, collide here and pick off this proton. So if this oxygen picks up a proton and this oxygen loses a proton, the next structure I could draw would look like this. Now, these oxygens would be shuttling their protons back and forth. But then either of these OH groups can swing an electron pair in and push out the leaving group now that has the positive there. So when those electrons swing back in, I get a protonated carboxylic acid and an alcohol. Then a water could pick off this proton. Right? So the net reaction here is this ester is converted into a carboxylic acid and an alcohol. Notice under the acidic conditions, every intermediate was positively charged. A single positive charge, right? There's nothing that has 2 positives at once. That'd be really unstable due to all the extra repulsion. There's nothing that has a negative charge because we've got excess protons around. Right? So really, hopefully that can help you with these mechanisms. Make note in your mind, when you see any acid present, you're pretty much going to be going through positively charged intermediates. Alternatively, as we were saying initially, if both reactants are neutral, then it would start too low in energy compared to the transition state. It would be too slow and the activation energy would be too high. So what we did here was we said, well, one of our reactants, we can start with a positive, and that would start higher in energy so it can get to the intermediate more often. The alternative would be to start with one of my reactants with a negative. Right? So since this already has a negative, it's not going to be that stable. It's going to be relatively unstable. It's a strong nucleophile. Again, I can't also add an acid here, because if I try to add an acid, well, the OH minus is just going to pick that up. They'll just neutralize each other, and that defeats the purpose of it. So when I'm under basic conditions, I'm not going to be forming positives, I'm going to be forming negatives. And so this is unstable, it's relatively high in energy to begin with. So its attack to push electrons up here and form this intermediate doesn't require that much energy. When the intermediate and the reactants have the same quantity of charge, there are going to be subtle differences in energy based on entropy, solvation, potentially resonance, and the other factors that stabilize negative charges. But as long as the quantity of negative is the same, they're going to be at least similar enough in energy probably to get from one to the other. Then this pair of electrons can swing back in and push out this leaving group. It's not a great leaving group, but it's all relative because once the leaving group leaves, it could come back in and do the reverse reaction. But really, what's most likely to happen here is a proton transfer. I've formed a carboxylic acid. This OR group is a really strong base. Proton transfers usually happen quickly. So what would happen is this would come in here quickly and grab that proton. And once that forms a resonance stabilized negative charge, that really is going to be where the equilibrium ends up because that is so much more stable. So again, we're substituting the initial group that was attached to the CO double bond for a different group, using a nucleophile to replace the other group and have the other group act as a leaving group. So I've been preaching to you about how we want to avoid intermediates with two formal charges. There are exceptions to that, and here is probably the only exception that you really need to know that is an exception to that idea. So in this situation, the nitrogen is in this sweet spot. It's got an electronegativity sweet spot, meaning that it's more electronegative than hydrogen. It doesn't have to be hydrogen, it could also be an R group. It's more electronegative than carbon and hydrogen by a fair amount. So it's really attracting these electrons and creating a nice large partial negative, which will allow it to attract to the nice large partial positive here. So it's high in electronegativity, enough to attract electrons and create a partial negative, but it's not too high in electronegativity. If it were too high, then it would also attract its lone pair too strongly and it wouldn't be willing to share it. And so it's a sweet spot because it's high enough in electronegativity to carry a large partial negative, but low enough in electronegativity to be willing to share those electrons and take on a positive that's not really that unstable. A nitrogen with a positive charge is relatively stable as far as charges go because it's not super electronegative. It doesn't like rip the electrons right back. It's cool sharing 4 pairs of electrons at once for the most part. So in this equilibrium, if the nitrogen attacks here and as these arrows are showing and pushes the electrons up to get this intermediate, well sure, this electron pair could swing back in and push that back out. So it's definitely going to be an equilibrium situation. But instead, what could also happen are some proton transfers. Right? So another molecule of the NH3 could pick off one of these 3 protons, and those electrons would stay on the nitrogen. And so that could give an intermediate that would look like this. Now there's only one charge, so it's a lot more stable. Now it can swing in and push out this leaving group. And that would be favored by entropy because now I'm forming 2 molecules rather than 1. It's not really favorable to form the new pi bond here versus sigma, but CO double bond pi bonds are relatively stable as far as pi bonds go. As we know, there's an extra resonance contributor that happens here that helps to stabilize the structure once the nitrogen's lone pairs free up and the CO double bond forms. This oxygen could come back in, it could go back. I mean, so it is an equilibrium. But in the end, the extra resonance that the nitrogen's lone pair engages in really does help to stabilize this structure. And so that would be the end of that reaction. That OR would then have to be protonated somehow to become more stable. So maybe you could add acid in the second step or something. So the point here is, even though most of the time you don't go through an intermediate that has two charges, if your nucleophile is one of the stronger nucleophiles of those that don't have a negative charge, like we could say it's a stronger neutral, it's one of the strongest nucleophiles that actually doesn't have a negative charge, that, and it can stabilize a positive pretty well. It can come in there enough, often enough, to create enough of this intermediate that after a proton transfer, electrons can swing in and give you a product. So this might not be the fastest reaction because there is a pretty big difference in stability between my reactants and my first intermediate. So the first transition state is going to be pretty high in energy. But it's not prohibitively high. It will happen often enough that over enough time, the reaction can go forward. So a couple points about these mechanisms. A lot of times there are proton transfers involved. So just to point out this mechanism here, it was relatively straightforward. The minimum number of steps is going to be 2 in any nucleophilic substitution on a carbonyl carbon, right? The nucleophile's got to come in, push electrons up, and at the very least, electrons have to swing down and push out the leaving group. So 2 steps minimum. This one, after that occurred, then there was a proton transfer. So you want to be aware and look out for proton transfers occurring in addition to the minimum number of 2 steps. Right, so let's just look at an example where we have proton transfers occurring throughout. And we already did, but I'll just show it again. So let's say we have 2 neutral reactants. So let's say I've got an OR here, so just put an ethyl group there. And want to react that with say we want to react that with water. So these are both relatively stable and not very reactive. So we don't expect the nucleophilic attack to happen first, because if it did come in here and attack, I'd get 2 formal charges from 2 neutral species, and that would be a big difference in energy and wouldn't happen very often. So I would also add some H3O plus to help make this a better electrophile so the weak nucleophile can attack it. So this would pick up a proton. Then the water could attack. And so the first step was the first proton transfer, and now we're doing the nucleophilic attack, pushing electrons up. And so the next thing that happened here is going to be a proton transfer. And in fact, actually, we're going to have 2 of these. So this isn't always going to be the case that things will happen in this order. We're just showing examples of how there may often be a lot of proton transfers involved in these mechanisms. So to stabilize this positive, a water would have to pick off this proton. That would give a relatively stable intermediate. What's wrong with this intermediate? Why wouldn't this be the final product? Well, we've got sigma bonds that are more stable than pi bonds, but we've also combined two structures into one, which isn't favorable by entropy or sterics. And so what would be more likely to happen here, especially since this water picking up a proton makes more H3O plus, is protons are going to continue to shift around, and this oxygen is going to pick one up. So in this case, we have two proton transfers occurring between the nucleophilic attack and the loss of the leaving group. So then the loss of the leaving group will always involve electrons shifting in to reform the CO double bond and pushing out a leaving group. And in this case, the product that's produced still has a proton. So we need one more proton transfer to regenerate the acid catalyst that was there and to make the final product. So we've got 1, 2 products, and then the H2O picks up that proton to regenerate the catalyst. So you want to do, a fair amount of practice with those mechanisms. So let's take a look at another example here. Here we have an acid chloride reacting with water. So what do we expect to occur here? Well, the acid chloride, as we said, is especially electrophilic. And we said because of the extra induction there from the chlorine, making this a larger partial positive, the chlorine can't really shift electrons in the resonance because of the mismatch in the orbitals to stabilize that positive. The chlorine is a single atom, so it's not very sterically hindering at all. And so the large partial positive here is actually going to be pretty good at attracting this water molecule in there. So we could add an H plus for this oxygen to pick up and make it attack even more readily, but in this case we don't need it because the acid chloride is already relatively high in energy with a large quantity of partial positive, larger than average. It should attract the partial negative of the water in there. So I guess here's another example where sometimes I tell you things and then show you exceptions to those things right away. And that is, in this case, a situation where we might form two formal charges on the same structure. We really should avoid situations where we have two formal charges of the same type of charge, right? Two negatives or two positives would be really unstable. But a positive and a negative, they attract each other. They're not prohibitively unstable. So then what would happen due to sterics and entropy is this electron pair would swing in. Once it swings in, it could push out the water, which means this is reversible, but the chloride is also a really good leaving group, so it could push out the chloride. So then, to get to the products, the chloride has to act as a base and pick off this proton. And that's how I get HCl. So will this reaction be reversible? Yes. The oxygen here could pick up the proton from the HCl and go back here. The chloride doesn't have to pick up a proton. It could just attack as a nucleophile and go back here. The oxygen could swing in and push the water out, which would go back to the reactants. So this whole thing's reversible. It's probably a little slow kinetically because we're going from reactants that don't have any charges to an intermediate that's got two charges, so as far as the reaction coordinate diagram goes, the reactant's relatively stable compared to the first intermediate, be pretty high in energy with its two charges compared to that. So the activation energy of the slow step, which would be the first step, is pretty high. It's not going to happen that often. But if we're really interested in what conditions would favor the products, we're not really interested in the kinetics. We're interested in just comparing the reactants versus the products. And when we do so, the reactants are pretty high in energy because of all the partial positive there. So that's starting off kind of high. The products also have something that's relatively unstable, right? We know HCl is a strong acid. It's not a very stable compound. It will very readily start protonating things. So that's also probably pretty high in energy. So when the reactants and the products are similar, it's hard to say which is more stable than the other. We might end up with an equilibrium that evenly favors both sides. So we want to look for conditions or strategies we can use to shift it to whatever side we want. So if we wanted to shift it toward the product side, what can we do? Would adding a catalyst help? No, because the catalyst would only shift it back and forth faster and get it to equilibrium sooner. The catalyst is not going to favor one side or the other. If we want to favor the product side, we've got to either use Le Chatelier's principle or somehow change the structures of the reactants and products so that the energy difference between the reactants and the products will change. So we could use Le Chatelier's principle. Using Le Chatelier's principle, we could use excess of the water. It's a reactant. Using a large excess of a cheap reactant should shift it toward the product side. We could also remove a product. Which product would be most easily removed? Well, sometimes when we're talking about removing something, we're talking about physically, like boiling it out, precipitating it from the reaction. In this case, though, it might be a little challenging to remove them physically. So instead, to remove the product, we could react it with a base, right? We know HCl is a strong, unstable compound, and that's why it's high in energy in the end. If we were to add a base, something that could pick up that proton and allow the HCl to give up the proton and react as an acid, that would make the products a lot more stable, which would be much more likely to give me a negative delta G and make the processed product favored. So we would remove the product by adding a base for the product to react with, right? The only way this can go back is if the carboxylic acid picks up a proton and goes back to the last intermediate. But if we use a base to pick up that proton instead, the carboxylic acid won't be able to get it. So typically when we react these reactions, often pyridine is included as a base. I'll just write that here, like pyridine. And just to remind you, pyridine looks like this. It's a weak base, right? The nitrogen can pick up a proton and stabilize a positive charge fairly well. Let's take a look at another example. So here we want to take a look at this mechanism. In order to facilitate this reaction, we might use a little strong acid, right? So we might add a pinch. It's going to be a catalyst, so it's going to be regenerated. We don't need much. But if we add a pinch of H plus from maybe some sulfuric acid, that will cause this oxygen to pick up a proton, and maybe one of these oxygens pick up a proton here. That's going to make this a lot more electrophilic. So since I had two neutral reactants, and there's a fair amount of sterics around here, getting them to collide and produce an intermediate with two charges, probably not very likely. So using a little acid to really facilitate this, get that positive to form, will really help to entice the nucleophile in and push electrons up to stabilize that positive. So now we've got an OH here. Still have a methyl group. And we have this oxygen which came in with its ethyl group. And it's now forming positive because it now only has one lone pair. So when we're using an acid catalyst, usually there's lots of proton transfers, right? We saw that mechanism a minute ago with all the proton transfers that occurred there. So probably a water is going to pick off this proton to bounce the charge there on that structure. So now I've got this kind of big structure. It's got a fair amount of sterics now because there's all these R groups in close proximity. Doesn't have very much entropy because I combined two structures to make one bigger structure that has limited ability to move around and be positioned in space. So what I would expect here probably is for a lone pair to swing in. Oh, actually, let me take that back. Since this is neutral and I have an acid catalyst, probably this carbonyl would pick up a proton first from the acid catalyst. So I don't want to run out of space here. So let's just show that now bonded there. That's going to make that positive. So then these electrons are going to swing in here. This is going to act as a leaving group and push electrons onto that oxygen. So this now opens, breaks open the structure. These electrons swung up there. This oxygen picked up a proton. These electrons swing in there. These electrons swung in here. Still a methyl group attached here, and the OET. And I have a division meeting to go to in 15 minutes. All right, so what's going to happen next? Well, we've got a positive here now. Probably this will be deprotonated, and that will become one of my products. So I might expect this oxygen here maybe to pick up that proton. This one will become this product. This one will become protonated. Now it's more electrophilic, and so since I'm using excess of this, I expect another one to come in here and push these electrons up to that oxygen. So this oxygen coming in there, it's not going to be bonded there. So now I've got a positive here. So now there are going to be some proton transfers. I don't have space for all the steps, unfortunately, but you want to imagine another molecule of ethanol picking off this proton here. So these electrons will stay behind and neutralize that. And then we're still going to have protons around because they just keep getting shuttled around. It's a catalyst, it keeps getting regenerated. This oxygen here is going to pick up a proton, making that a leaving group. And then an electron pair will swing in and push that leaving group out. So that will produce a water. And this structure will look like this. This electron pair gets swung back in there, so it reforms a double bond. And I still have the OET there. And so then this proton will be picked off by ethanol, and that will give you the other product. So what we're seeing here is when you have an anhydride, and an alcohol in excess and a little acid catalyst, you can get the alcohol, in essence, to attack both of the carbonyls, not at once, obviously, one at a time, pushing out the leaving group, which we saw here is a nice leaving group because it's already positive and it stabilized the electrons that are given, and you get two new esters forming. Each ester results from the ethanol attacking the respective carbonyls and end up getting connected to those carbonyls. And as we were saying, we would add an H plus to facilitate that reaction, but that's a catalyst. So that only helps the kinetics. Can we help the thermodynamics by making the equilibrium favor one side or the other? And the answer there is also yes, because we're using an excess of reactant. Using an excess of reactant by Le Chatelier's principle helps to shift the equilibrium more toward the product side. So we might use that, as we were saying, as the solvent in the process to help shift the equilibrium toward the product side of that. The whole process would be at equilibrium. And that's where we needed to get to today. So practice up there. And on Wednesday, we will, I believe, finish out this chapter. So we'll be talking a little bit more about some of the carboxylic acid derivatives and how to make them and interconvert between them. And that will be really useful when we're looking at syntheses moving forward, because especially the acid chloride, if you can figure out how to make it, as we showed today, it can be used to make a variety of other substances because the chloride is such a great leaving group. Once you've made an acid chloride, any nucleophile can come in and replace that. It gives you a lot more control over the structure of the product that you might be making. Alrighty, another day in the books. Please let me know anytime anyone has any questions.